rename it, all right.
Yeah.
Stephen, the left, like. All right, welcome everyone to the last lecture of this workshop.
I feel like that before, but
Also, it's a Russian. I don't know if the workshop going on at the same time.
so what?
It's a Russian points workshop is also happening at MSRI at the same time.
In spring 2023?
Yes,
Is it part of this program?
it's a separate program.
Oh, there's two programs at MSRI.
Yes, which are all about both about numbers.
Okay, okay. I don't know this. Okay, what's it called? Rational points or something?
Russian points.
Well, it's like I'm schooling this in March.
Okay, so point something. Yeah, I just wanted to advertise. For the rest of this kind of workshop you can go to maybe in the next year. Berkeley, California has a research institute called. It has a new name. It's like the. I forget what it is. There's two people's names associated with it now because they gave some $1 million or something. $10 million or something to the Biomedical Sciences Research Institute, and so now it has the name Simons attached to it. Hedge fund billionaire, and there's another name. If I feel bad that I can't remember it, although I don't. They have plenty of money. I don't feel that bad.
Lauper.
But there's a whole what?
Simons and Lauper.
Simons and okay, yeah. So, anyways, in spring 2023, there's an entire semester program at MSRI. It's too late for you to apply to go for the entire semester. But during these semesters at MSRI, there's workshops, 3 of them, maybe for each program, so maybe there's going to be 6 in total. And the funding deadlines I checked this morning for the spring 2023 workshop are all in October. Okay. And then there's also a 2-week workshop. In March 2023, that'll be held in Heidelberg, Germany. And the title of the workshop is Non-Archimedean Geometry and Eigenvarieties. When you Google it, I didn't quite find the website, but if you go to the website of Judith Ludwig, who works at Heidelberg, under miscellaneous on her website, you can find a link to the website for the workshop, and there's also funding opportunities for that due in October 2022. So I don't know if you'll see me in Berkeley, but you will see me in Heidelberg, at least if you come for one of the weeks. I'm not sure whether I can get away for both weeks. Okay, so that's that. This is my 4th lecture, and what I want to do in the 4th lecture is maintain the sense that this is a school and teach you some of the theory or explain some of the theory you would need to prove this variational statement about Galois representations on an eigenvariety. As opposed to throwing at you a bunch of big conductors and stuff like that. So let me remind you of this eigenfamily I constructed, and I'll say it aloud one more time. The word eigenvariety refers to what happens when you take these little families that I build over small balls and you glue them all together. And you build a single kind of object. But I focus only on the local picture. And I focus on DL2 for the first 80% of the lecture. I need a cut form an eigenform for the heck operator at P and also the heck operators away from P. And then we've discussed how to construct roughly a finite map from a space V to a subset U that's open in the p-adic weight space. So there will be a point on here, VF corresponding to your eigenform, and it'll map to the weight K inside the weight space. And now I stop writing the lambda K and all this stuff. I just write K for the integer. You can identify the character. And there's like a universal eigensystem. Eigensystem, which seems like a complicated word, but it just means a system of eigenvalues. That takes a heck operator and gives you an analytic function on V. That's what that ring is. Algebra, QP algebra. Such that here. When you take a little point in the big space V, the H1 of the modular curve at level gamma 0 NP, coefficients in this big distribution model at the weight lambda V has a non-zero eigenspace for the Hecke action once you evaluate the universal Hecke eigensystem at the point V. And then the goal of the lecture is to explain the kind of mathematics you would have to invent to construct the Galois representation, rho big V. So I put little lines here to indicate those are to be capital. I'll call it rho V universal. It's universal for V. This will be a representation of the Galois group of the rational numbers to GL2 of the ring of functions on V, which is unramified at L not equal to NP. And the trace then of pervenience elements at L. So you take this element in the Galois group, well defined with the conjugacy, the trace will then be a well-defined element of the analytic functions on V. And the analytic function you could get is the one you get by evaluating the universal eigensystem at the CL operator. CL. Now, one thing I really have to do that logically in my 4 lectures comes in the first lecture, but I don't mean logically. Like logically, it's not missing, but somehow educationally, I missed a remark in the first lecture. Let me make it now about all of these conditions on the traces here. So if I let Q and P be the maximal extension of Q inside the algebraic numbers, that's unramified at L, not dividing the finite set of primes and P. Then a theorem essentially of Tropicaro tells you that the conjugacy classes of the pervenience elements are dense as a set inside a topological group. And the group is the Galois group of this maximal unramified extension, which is a quotient of the absolute Galois group through which any representation unramified away from NP factors. So these representations only depend on factoring through this group. And inside this group, the conjugacy classes of the Frobenius elements are dense. They're the closure of the conjugacy classes of everything. At the finite level, the Frobenius elements hit every conjugacy class, but at the infinite level, you get a density statement instead. And so, if rho is, say, continuous, and maybe irreducible, just make things as simple as possible, valued in some field K. So K here is some topological field. Then there's separately then a theorem in representation theory that goes by the name Brouwer-Nesbitt that tells you that rho is determined by the characteristic polynomials for Frobenius elements. I'm not dividing it. So the characteristic polynomials are well defined because they're conjugacy invariants. And here I should say that NP here should be the same NP. So unramify. I'll not dividing NP. Any characteristic zero, like the representation that I've mostly been working with, you don't need to take the whole characteristic polynomial, but rather just the traces. And so every time I've been writing down the trace of the L representation and kind of just telling you that information, I've been uniquely identifying it up to whether or not it was irreducible or not. Okay. And by the way, the representations associated with club forms on GL2 satisfy that irreducibility hypothesis in characteristic zero. So the reason I say that is if you don't know this already, then it's a little bit hard to digest the construction of what's called a pseudo representation and what kind of data that actually contains. So let me tell you then what a pseudo representation is. And the reference for this, which I think everyone has to read at this point, if you want to study this particular kind of problem that I'm suggesting, is a paper of Chenetier that begins with the p-adic analytic and then continues the p-adic analytic space of pseudo characters on rigid spaces or something like that. And what's really nice about kind of doing this at the end is this is actually like almost pure algebra what we're going to talk about, and so really you can kind of separate your mind a little bit from all the automorphic forms and just like do some algebra exercises if you want to understand Chenetier's paper.
Algebra means that you can replace, just for the students. What do you mean by algebra?
I do it here.
You can replace the group by any gamma.
Yeah. So A is going to be a commutative ring with 1, and G is going to be a group. And I phrase everything in terms of A and G, and then I tell you where continuity and those kinds of things matter. Okay. So then Chenetier made a definition that there's a long history that I'll mention, but I start just with Chenetier's definition. So an n-dimensional pseudo representation D, and I'm going to write it from G to A. So there's an underline on the D, and that's to remind me that it's like a collection of kind of objects. Okay. And it's not a function. Like you'll see what it is, but it's not a function from G to A. The way, yeah. Let's just tell you what it is. So the first thing is that for any A algebra B, you get a map called DB that takes the group algebra of B, the group algebra of G with B linear coefficients to B, and this could be a multiplicative map, a multiplicative set. Okay, so it just associates any element of the group algebra and element of B in such a way that when you multiply in the group algebra, you multiply inside B. Number 2. is that the assignment of B goes to DB could be functorial in B. Okay. B maps to B prime, and these are both A algebras. Then you get a diagram like this. So if I call this map F, then F introduces a map on the level of group algebras by just changing the coefficients, but keeping the group the same. And you have your map DB, and you have the map F again, B prime, and that square should commute. That's the second axiom. The third axiom, so I haven't mentioned the n at all. Let me put it over here. The third axiom is that if B is in B, then dB of dx is d to the n dB of x when x is an element of the group L. Okay. Now the definition I've given is really due to Navier in this paper, coming in 2010 or about there, but it's a 30-year history beginning with a paper of Andrew Wiles in the 1980s, where he defines the notion of a pseudo representation in 2 dimensions with the task of constructing Galois representations. And it's remarkable because as with most things that some of the strongest researchers do, the definition isn't even made. There's no definition in the paper that I'm referring to. It just shows up in the middle of the proof, and he's just going to consider an object like this, and I'll call it a pseudo representation. Richard Taylor took the notion and formalized it and created a section on another paper for homocomplex forms. He did this, and then there's entire work. I mean, there's a lot of work in the 90s and 2000s generalizing this notion. But the early notions didn't have in mind this whole DB, which will turn out to be like these characteristic polynomials rather than just the traces. And one of the problems Navier was trying to solve was making a theory that would be insensitive to the kind of coefficient fields you have here. So Navier's theory is extremely general, and that's why I say any commutative ring, and I don't add any hypotheses. Let me give you the main example. I might have just gotten ahead of myself. Are you okay, Arthur, with the definition?
Yeah.
Okay, sorry, I thought you were giving me eyes a little bit, so it was good.
Allergies.
Allergies, no, that's fine. I rewrote, like if you look at Navier's paper, the definitions won't, there will be 3 axioms and they'll be slightly different, and I just had to try to simplify them for myself. So the main example will come from a representation. So suppose you take a representation of your group P valued in Z ln of A, so linear representation, then it defines it what's called a representation of algebras, rho B, from the group algebra to the n by n matrices by just sending an element of the group algebra to what happens when you take the various matrices here that you get from evaluating the representation on the group. And it's no longer sending it to invertible things because you have all this linear adding going on. Like you add to invertible matrices and it might not be invertible anymore. And then you set dB to be the determinant of rho B. So if you look at Navier's paper, he'll define these called determinants. Okay, that's what he calls them, because he doesn't want to overwrite the notion of pseudo representation, which was already there in the theory. But very shortly after, people forgot this, and most people call them pseudo representations now. I think it's fair to say. So, anyways, this is the map from BG to M out of B goes to B that you get by taking rho B here and then taking the determinant there. Lemma B goes to DB, define the pseudo representation. And I don't know what I could say that you can't say just as quickly in your head. Like determinants are multiplicative, and rho B itself is an algebra map because it arises from a multiplicative morphism of groups, and so on and so on and so on. Okay, the homogeneity is the scalar law for determinants. this N. Now, for example, though, like you might ask why I even did the B thing. Like, why not just take only A? Right? Why extend scalars to B and make this thing up all in B algebra? I mean, that sounds a bit fancier than it needs to be. So, on the other hand, when you allow that, you get objects that you may not realize. If you only stick with A, you only have the representation. But if you have the elements G and G, then you can take the pseudo representation and you can plug in the A algebra given by polynomials over A in a single variable. You're then allowed to evaluate this on any element of polynomials and the group algebra. So I can plug in X and I can plug in G and I can subtract them like that. And when you do this, so you should check this. This is the characteristic polynomial of the matrix rho of G and type D on A. And so this way of allowing kind of not just a linear coefficients, but kind of any A algebra coefficients gives you an algebraic way of accessing these characteristic polynomial from a single structure. And then given any G, given any D, we define phi D, D comma X. See what happens when you evaluate the pseudo representation on the element X minus G. You get a polynomial this way called the characteristic polynomial of X. I did want to say, so a determinant, a pseudo representation constructed this way, we might say come from a representation. And there's a theorem that I think we don't logically need, but is important for your educational experience if you're going to go into the field, that in fact, when A is an algebraically closed field, then every pseudo representation arises from a representation in this way. As long as the representation, it arises from a unique semi-simple representation. Okay. So that's one thing that you can be aware of. Yeah. So here now I'm going to move into some other pseudo representations, but I want you to notice the connection here between the idea that there's something called a characteristic polynomial of the pseudo representation and these characteristic polynomials here that are uniquely determining the Galois representation. The theorem I mentioned about algebraically closed fields and any pseudo representation arising from the determinant of a representation is a really important theorem. But I think for me, the core feature of a pseudo representation that a representation does not have is what I call the ring of definition, or the theorem on the ring of definition. I mean, this is not something you'll find in some paper called something, but it is one of the fundamental properties of these things. So suppose you start with your ring A and a pseudo representation over A, and you have a subring A prime. And suppose also that when you take the characteristic polynomial of any group element, that lies in the subring, polynomials in the subring. Then D kind of factors through the subring. So then D factors through the subring for some unique D prime. So there's a determinant, a pseudo representation. Sorry, now I just told you that I'm going to use a pseudo representation and I'm using the determinant. A pseudo representation, D prime from G to A prime, So the D itself is the composition of that one, and then unique kind of includes it. And if you think, okay, yeah, if you have some remorphism or something that lands at A prime, then of course it factors through A prime. Like this kind of thing isn't true if you only look at these kind of characteristic polynomials for actual representations. You take G to be the real numbers, mapping to GL2 of A, which is GL2 of R. So I'm trying to be careful. There's two copies of R on the board. One is my G and one is my A. And this sends the element X to 1, X, 0, 1, a kind of non-semi-simple matrix, because it's a non-semi-simple matrix. Then the determinant of rho, like in the sense of this example, is defined over T. But rho is not. And so these pseudo representations, by this lemma, have the ability to define over a subring, even if the representation they arise from cannot be descended to that subring. Okay.
Good question.
Yeah.
So in the case where, I mean, like, so in some cases you do have these theorems where you actually can descend the representation, like, I guess maybe for like fields or something like that. In cases like that, do you have, like, where your field is not algebraically closed, do you have, like, or I guess how general is this, like, equivalence between then pseudo representations and representations?
So over an algebraically closed field,
I guess I'm thinking for like
n-dimensional pseudo representations are equivalent to semi-simple representations of a group.
yeah.
And otherwise, I mean, if you have representations over value to say a finite field or something, and you know all the characteristic polynomials, then you kind of know the representation as long as it's semi-simple.
Yeah.
By things like the Brouwer-Nesbitt theorem. Does that answer your question?
Or I guess I'm thinking like, I mean, in some cases you have this like Carrier lemma where like you can like you can descend like for like subrings for like complete Ethereum things.
Yeah. Just an actual representation.
Actual representations. Yeah.
Yeah.
Yeah. So is there some sort of like, can this be? Is there a way on like is there some sort of like more specific connection between representations and pseudo representations in a case like that?
I don't quite know what the general statement I would want to make it, but let me just point out, like, if you have a representation defined over some bigger than A, and there's a subring A prime where this is happening, and separately you can just have a representation to A prime for some reason.
Yeah.
You just send them both, and then if the thing is semi-simple, they have to correspond to each other by more kind of pure abstract algebra. Does that maybe answer? I mean, if you wanted to know the exact statement,
I guess I'm asking you, can you derive a Carrier lemma from like something set just purely in the maybe it's not. Maybe I just can't.
yeah, I'd have to take the task of looking at this thing called the Carrier lemma, which I kind of know what you mean, but I don't know the precise statement off the top of my head, and I'd have to then that's some long improvement in the 80s, from the 90s, and we have to trace the literature forward to see exactly that kind of thing. I mean, I'm trying to remember even if in practice that lemma is proven by some kind of lemma like this first, that you first descend the pseudo representation, and then if in contemporary references they'll prove that kind of lemma using this machinery already. Yeah, there is a version of that kind of thing that I'll state for Henselian equivalent. So yeah, and let me just mention here this notion of continuity, because you could imagine, for instance, G is G here is a topological group and A is a topological ring. And then you might want the notion of a continuous pseudo representation. So continuous means that the function that sends G to its characteristic polynomial inside A of X is continuous. Where implicitly here, there's a lemma that these characteristic polynomials don't just land inside some random polynomials, but they're polynomials always of degree n, where n is the dimension of the pseudo representation. Okay, and that's based on this homogeneous thing. And so the topology on A of X is like the topology on a to the n or a to the n plus 1 or whatever it would need to be here. And then this lemma holds. For continuous b. If the hypothesis, sorry. If a prime is an A and this lies in here. For every element of the group, maybe naturally you already assumed that, but if you want to do it for continuity, you don't need every element of the group, you only need a dense set of the group. Be continuous. And put it in quotes here for every G inside G prime. The dense in G. And it's never quite apparent when you see definitions like this, like there's these three axioms and kind of how are they interacting. So what I want to do, just I don't know, I don't think it'll take long, and I want to explain this lemma, or at least a plausible version of the lemma, like in one instance. So the lemma is telling you that you have, for every element in the group, certain elements that you get by evaluating the pseudo representation, they lie in a subring. And what you need to prove is that, in fact, no matter what kind of polynomials you evaluate your pseudo representation on, kind of no matter what b you use, it kind of lands inside b prime in some sense. Like it lands inside a linear things you get from extending scalar from a prime to b rather than a. And so let me just show you how that kind of thing works. Calculation. When n is 2. So what I want to look at is d of ax y h of x plus gy. So that's the kind of thing you can plug in to a pseudo representation. You can take the algebra of polynomials and two variables, and you can plug in something like this, where h and d are in G. And I want to claim that this lies in a prime adjoint xy. Okay, notice there's two variables here, and my hypothesis is about one variable function of this x. So I'm going one variable higher, and that's what I want to explain. Okay, so, and I'm going to highlight the axioms. So the first fact is that this equation can be calculated the following way. So this, whatever it is, will always be equal to dA of h x squared, that's the 2, plus some function f of g, f of h g xy plus dA of g y squared. So when you evaluate a linear polynomial on x and y, what will come out is a homogeneous polynomial of degree 2 in x and y, where kind of the x term only depends on this coefficient and the y term only depends on this coefficient, and then there's some cross term. Okay, and this is using axiom 3, more or less. So the homogeneity here is why you get a homogeneous polynomial. And so then the assumption is that when you take this equation, I'm going to call it star, and you evaluate it as h is the identity element and y is -1. Okay, that's how you get the characteristic polynomial, which are the x minus g's. This is then x squared. The determinant on 1 is 1, or the pseudo representation. You get minus f of 1 comma g x plus d of g lies in a prime of x. So that's kind of what you know. Lemmas, or from the from the assumption in the lemma that the characteristic polynomials like that. And here, let me just emphasize, this is where you're using, and you're implicitly using it here also, but this is where you're kind of using axiom 2. Then there's naturality. So when you evaluate on the outside of an equation, it's the same as evaluating inside the equation. Sorry, it's right here. This is what I meant. All right, this is how I evaluate after taking a pseudo representation. And what axiom 2 is saying is I can evaluate the polynomial on the inside first. And so then you can use the multiplicativity in axiom 1 to in fact see though that star is also equal to p-adic h times x plus g over 8y, which is then equal to dA of h times this whole thing, x squared plus f of 1 g over h xy plus d of d over h y squared. Applying this observation with g over h rather than g, what you learn is that this lies in a prime of x y actually. And since you already know that this lies in a prime by the same thing, what you get is that this actually lies in a prime of xy. So I explained this on this one board that using the kind of the one variable hypothesis here, you can get that any linear polynomial in 2 variables descends to a prime rather than a. And then you have to think like how to reduce questions about 2-dimensional pseudo representations to just 2 linear variables like this. Okay, and in n-dimensions, the calculation is a bit more complicated, but this is kind of the rough scheme that you would want to follow. And that was my one example where I can kind of show you theoretically how to access some of the axioms you see in this definition before I erase it. So now I want to say the results that's proven in Geneviève's paper. All of this is proven in Geneviève's paper by scratch. Well, he built these notions of pseudo representations on prior notions, but because he completely changed the definition, he had to reprove everything. And so the reference is really good. If you reprove everything, there's no back references of the older papers. I mean, it's like I don't want to compare it to easier. I didn't need an E. Okay, so it's going to give us the theory of schemes, and you have to reprove everything about algebraic varieties in the language of schemes. This is a much easier version of that story. So pseudo representations in an eigenfamily. Let me tell you the main result you need to know. And this might go to maybe what Juan was saying about lemmas about pseudo representations over complete local invariant rings. So the proposition sorry. Oh, let me get to Juan's comment in a minute. I wanted to apply this lemma. So here's the lemma about the rings of definition. And what I want to do is rather than construct this Galois representation first, what I'm going to construct is a pseudo representation before I try to construct the representation. So the rest of the so the first step proving this is the following. So suppose I start with F, B, etc. as in the theorem. Then there exists D there's just a unique D, which is going to be a pseudo representation on the absolute Galois group, valued in my ring of analytic functions of O, which is unramified at L not equal to NP, where that means it factors through this quotient, right? So I raised the definition, but somehow the D is involved in the definition, and I just mean all of the DGs factor through that thing. And the characteristic polynomials of this pseudo representation evaluated on a Frobenius element, which one, I think characteristic polynomials will be conjugacy invariant automatically, is going to be equal to x squared minus psi of TL x plus lambda of L. Okay, where lambda of L means, you have this map from B to the weight space, and lambda is like a universal character over B, evaluated at the element L. And the really important thing to pay attention to is the psi of TL. So this says that there's a pseudo representation valued in the ring of analytic functions on the eigenfamily. Okay, and the trace term of the characteristic polynomial is the eigenvalue varying analytic over the time. Okay. Good. Let me explain why this is true. So why? There's three main steps to the argument. And the first step is the one that is going to fail if you try this in other situations sometimes. So what I want to do is I want to look at Z, which is going to be the set of points in my eigenfamily, whose weights are integers k prime that are bigger than k. Okay, so I look at my family, remember my eigenform is weight k, and I look at all the points in my family lying over weight k prime that's just bigger than k. And therefore, because it's in my family, highly congruent to k mod some power of p. And then given v prime, so I didn't write this in my review, but remember that as long as you're lying over one of these weights, the points are coming from classical modular forms. Okay, so given v prime, you get an f prime, that's the weight k prime plus form of gamma 0 and v. So eigenform. Like this. And from an eigenform, you have a Galois representation automatically. Not automatically, I mean, okay, then you have to construct those things, but you could have done that before you started constructing eigenvarieties. Moreover, because these weights k prime are accumulating at k in a p-adic topology, there's things arbitrarily close to k. The points f prime you're going to get from this process are going to be dense in the space D locally at the point f. So each row f prime gives rise to a row v prime that defined to be row f prime, L representation. And of the shrinking, this doesn't matter about shrinking, but Z itself inside V is going to be a dense set of points. Two kind of statements there. Good. So that's the first step. It's just realizing that if you take one of the points in your eigenfamily over a weight k prime, it has a Galois representation, and the collection of these specific points are going to be dense in your space, p-adically dense. Okay. And that's most clear maybe if you really in your mind picture V and U as being isomorphic under this weight map. Because then all I'm asserting is that the weights themselves are dense in the area around K, which is because integers are dense in the p-adic topology. Step two I want to apply my limit here, so what I'm going to do is I'm going to let A be equal to the following. So I take the product over my V prime, let me call it Z.
The risky dense or p-adically dense?
Yeah, so I haven't really been distinguishing between what kind of geometric spaces I have. But here it'll be Zariski dense in any neighborhood around the points. And so if like somehow some combination is determined very Zariski dense.
I'm just asking because, I mean, of course, around K, you're fine. But, you know, like one day people want to do this over the whole eigenvariety. And then the integers, they're not really dense.
Yeah, no, I understand. So the Zariski dense, and I'll tell you why. So let me write down the consequence. Yeah,
sure.
And let me tell you the consequence of this, okay? What Zariski dense means if I evaluate a function at the point in Z and it vanishes, then it vanishes everywhere. Okay? So what I do is I take my ring A to be the product of all the residue fields. At my points. And the density, so thank you, Melana, for asking me exactly what I mean, because like by density, what I mean here is that when you take a rigid analytic function and you evaluate it at all the points in Z, it vanishes there only if it vanishes identically. So that creates an injection from the ring of analytic functions into this product. Okay. And because I have all these Galois representations of the point in Z, I also get a pseudo representation defined over A. Defined over A, that literally is just like the tuple of the determinants of the row Z's, where Z is in Z. So each thing has a representation. I take the corresponding determinant, and then it defines kind of a product pseudo representation. Okay, but now, so this argument, by the way, is due to Schneider fundamentally. You're in the perfect position to set up this lemma, right? Because the lemma says that if you have a subring of a ring over which the pseudo representation is defined, and all the characteristic polynomials are defined over the subring, then the pseudo representation descends to the subring. So step 3 is that you just notice. So when you go back to how Galois representations arise, the Galois representations satisfy this equation evaluated at the point, right? The trace term of the characteristic polynomial is the trace of Frobenius, or the height eigenvalue, excuse me. And so that means that when you take chi d of prob Lx, this actually lies inside the ring of analytic functions for all L. By analyzing the classical Galois representations, and so by the lemma, d factors through L. Sorry, d factors through the actual ring, rather than just this entire product. And I mean, this is just a sketch of how the argument goes. There are some technical points about the various topologies on everything that I'm not going to highlight so much, because you have to use this comment of continuity, because of course I didn't say that every Galois element has a characteristic polynomial here. I only know what happens at the Frobenius elements, because that's all I ever write down for Galois representations. And I don't think a random higher. Good. And then to finish the proof, now I can explain the exact statement you need to finish the proof. Because at this point, what I've done, just to summarize while I'm erasing the board, I start with a modular eigenform, a coupled eigenform. And here, they have a Galois representation. I build a family of eigenforms. And over this family, I have some countable collection of points that are kind of locally dense around the one I care about that have Galois representations. What I do in all these limits is I glue together the characteristic polynomials of the previous elements into the structure of a pseudo representation over the analytic space. And that's kind of where I am. If you want an actual representation like I claim, then you need an argument like this. So the following proposition. So you start with a ring A now, which is now going to be my ring of analytic functions more or less. Oh, it's not exactly going to do that because it's going to be a local ring. So it's a Henselian local ring. And A mod NA is equal to L. And assume B from G to A is a pseudo representation such that when you like compose it with an absolute residue field, so residually it's a pseudo representation arising from an irreducible representation of the group.
Absolutely.
Yeah, maybe I make L algebraically closed, or it doesn't.
I mean, no, you can keep it up, but it's still be
Okay,
absolutely
yeah.
visible.
So that is that rho, or rho is absolutely irreducible, mapping from G into GL and of L. And in the application, I'm doing all two-dimensional things, but in practice, there's no difference in doing n-dimensional things. Then there exists a unique rho A from G to GLN A such that D itself is the determinant of rho A. Thank you, GLN. GLN. Okay. So this is kind of a lemma that describes the condition under which a pseudo representation arises from an actual representation. The lemma says that if you have a pseudo representation over a Henselian local ring, so a ring where Hensel's lemma holds, could be a complete local ring, for instance. And that pseudo representation, when you look at the residual thing, the thing over the maximal ideal, it arises from an absolutely irreducible representation. Then automatically the entire representation lists to the Henselian local ring. Okay. And so then you apply this to the thing I just constructed. So D maps the ring of analytic functions, which is not a Henselian local ring because it has lots of points. There's lots of points in V, but you can compose the ring of analytic functions into what you might call the local ring on the rigid analytic space. And it's a theorem coming from the way analytic spaces are constructed that this is a Henselian local ring. I got into an argument last time I was at Notre Dame with a colleague who's no longer here about why that was true. He made me find a reference basically, but somehow why this ring is Henselian. And so then by the lemma, or by the proposition, I'm not completing it here.
You're not competing?
No.
Oh, really?
If I wanted to complete, I would have to put a hat. I put a hat there, and I would have said complete. It's just Henselian.
You're sure you don't want to compete?
Well, let me just say the rest of the proof. So then the proposition implies that you get a Galois representation, rho B universal, valued in GL2 of that ring. Okay, but now if you think about like how a local ring on a geometric space is constructed as terms of functions, under some finiteness hypothesis, which will be satisfied in applications, that such a thing will always, like the matrices will always spread out to some small open set around the point. And so up to shrinking B, you can kind of spread out to an open neighborhood of B, like an open neighborhood of the points. Okay, and that's why I don't want to take the completion.
just roughly, I mean, like, because what's, this is not algebraic local ring. This is not completed local ring, so what's all ring, like how, this is like some kind of a limit over neighborhoods?
Yeah. It's the stock of the structure if you on the rigid variety. And if you wanted to try to take a Galois deformation here, you would have completed it at this step, so that you had a complete local ring, but it's not the main, it's not the main point of the argument to say.
Psychologically simpler, I mean, probably, yeah, in the way you set up your lecture, psychologically simple to complete it, just to be able to apply these propositions such as, and then quote Bergdall in the book that actually you can decomplete it once you have the government station.
Wait, why? I don't,
Because, but you're saying it's in Cancelia, but do you have a reference for that? Okay. So
yeah, I did, the last time I was here, I focused on someone, and they made me find them out, because I had two references.
Oh, okay.
There's one that's in a paper, Bergdall, and the one it is, the rigid local ring on a variety like this, is Cancelia, that's all the one that's had, it's not even, you don't even have to unwind it. And then there's another reference, in this, I don't know who the authors are, but it gets cited at DVP, it's like their initials or whatever, it's the book on rigid geometry. So,
In the future, you can see that the last two times you were.
This is the
yeah, no, that's true.
book. What? Vanderfoot?
Yeah. It's just all, I always know the initials when I get cited in the text, and then I know the text quote and stuff. Okay, so I talked for 53 minutes. That's the end of the argument. So I proved the theorem. After spreading out kind of the representation from the germ, from the ring of function germs to an actual open set. What do I want to do in the last few minutes? So let me just give you some numerology. I want to highlight something that happened in the argument. So for GL2, when you construct these p-adic families, the set of weights over which you work is an open subset of the p-adic weight space, and they both have dimension 1. And so the basic realization in this density step is that if you start with some k as an element of U, as algebraic, meaning it comes from an integer, then there's an entire open, then there's an entire collection of algebraic weights inside the set E. Okay, so then k plus, if I want to be really careful about it, you take k plus some power t times p minus 1, and you multiply by any positive integer, and that will also lie inside E. Okay? As a dense subset. And the Zariski or the p-adic topology on that open set. And this is that's what leads to the stuff in this argument where the set Z of modular forms over these weights are dense inside the analytic family, which then leads to the entire argument continuing from there. Okay. Now, when you work on GLN with n bigger than 3, bigger than or equal to 3, the basic theory always constructs families of weights and eigenvarieties over them that map finite to 1s. So U and V have the same dimension. Okay. And this, I'll remind you, are the characters on ZP cross the n now. So in particular, it's n dimensional. These weights, however, they have to arise from weights of cuspidal automorphic forms arising in the cohomology of locally symmetric spaces. And in Miladin's talk, you saw the symmetry equations involving an integer W. So in practice, the weight over which you work have a dimension that's a 1 plus the 4 n over 2. And that's just because it's the dimension of like a collection of lambda one to lambda n that satisfy a condition like lambda I plus lambda n plus 1 minus I is W lies in the integer ring independent of the I. So only half the weights matter, and then you have one extra parameter. And that's what these dimensions are. And so even if you have some algebraic weight lying inside U, if all you know about U is that it's some subset of this dimension, you have no reason to believe that U itself contains a then set of other algebraic weights. No a priori reason. For U to contain more algebraic weights. And so because of that, this argument for say just like the basic GLN eigenvariety where you just plug homology of the locally structured spaces for GLN into the eigenvariety machine, this argument cannot go through somehow. Because you're not going to be able to pull off this step where the automorphic forms themselves are dense. And so you're not going to be able to interpolate the eigenvariety in this p-adic sense. So then I just end with some closing thoughts. So there's two things you can do now. The first thing is you can restrict the automorphic forms that don't arise just kind of natively on GLN, but rather arise maybe from some other connected reductive group, which have some symmetries, in which case the entire picture changes and the weight space shrinks to become the dimension you want it to, and then you can pull off all the arguments. And this is the kind of thing that happens with these Shalika models, or if you ever hear unitary groups that are compacted in infinity, or definite quaternion algebras, like that's the kind of game that's being played, is massaging it so that the weights and the weight space, the U and the W have the same dimension so that you can pull off these density arguments. If all you care about is the fact that Galois representations vary over eigenvarieties, there's a more sophisticated version of this argument that was written down in a paper of Johansen and Newton. So they show the variation of the Galois representations for GLN over Q eigenvarieties by sidestepping the issue. And the key, I'll just say it out loud, is in the construction of the Galois representations for automorphic forms in this case, Peter Schultz's paper constructing them constructs slightly more Galois representations than you might think. It constructs things associated with what are called torsion classes in the locally symmetric spaces. And they use that crucially in these arguments. So let me, that's like a plug if you want to go read this. So this is an algebra and number theory in 2019. So this is very kind of modern stuff. And then the second comment I want to make is you might ask for versions of the infinite firm, these GLN situations. For to construct that infinite firm, I use this variational statement on Galois representations. And I'm kind of suggesting that I'm a little bit worried about it in general. So there's two papers that are very interesting and have not been mined for everything that they talk about. Okay, there's stuff in these papers that people have not really understood, I think. So Tenagier's paper in the Annals of the EMS in 2011, where he studies the infinite firm for GL3, except this transfer to a compact unitary group. And a paper of Hellman, Marjolaine, and Train that's like not even published, it's like to appear. Where they do some PLN thing on these complex unitary groups. Where the symmetries that unitary groups have allow you to avoid this kind of numerology in general, which is to say that the question for just like blanket GLN is kind of completely open and something you might think about over the next 15 years or something as you're developing as a researcher. So I'll just leave you then with an example. So in N is 4, if I figure out the numerology correctly. So if N is 4, then the numerology tells you that the various V's have dimension 1 plus 4 over 2, which is 3. Okay, so for GL4, you have 3-dimensional families. The X row bars have dimension 33 in that case. There's a whole lot of twisting, so don't think it's so big, but the X row bars have dimension 33. And there's these 3-dimensional families sitting inside there. And typically for a classical automorphic form, there's 4 factorial different ones, because they're the orderings of these eigenvalues in the Laplace form. So the number of these per pi is 24, which is 4 factorial, kind of generically. But there's no reason to like say, okay, of course, all of these V's will explain these 33 dimensions. You have 24 3-dimensional subspaces or a 33-dimensional space. They could arrange themselves in all sorts of configurations. And you're not going to get the kind of curves in a 2-dimensional space and you're talking orthogonally forcing everything to be dense. And even worse, if you don't have these kind of algebraicity density involved, even if at one point locally you could explain all 33 dimensions, you have no way to propagate along the different 3-dimensional families typically. So these papers get around that in these symmetric situations, but in general, it's kind of a wide open thing that you could think about, if you want. So that's all I'm going to say for my lectures. Thank you. And don't cite these numbers because I just did them on a napkin and I'm pretty sure they're right, but maybe they're off by 1 or 2 or something. Maybe I missed the factor.
4 factorial is 24.
This one these are I'm quite confident about. This one, I just wrote down the calculation. I've never seen someone say what that for large it looks like.
There's a question.
Yeah.
So wait, just a question about this. So when you're spreading out, are you just saying that the image is compact? In order to say that you can spread out, or are you using some sort of finite generation or?
Yeah, I mean, I think I'm using the image of Galois compact in there. And yeah, like I mean this group, like I'm using something about the structure of the Galois group that's maybe that it's more than compact. There's this conjecture, which I don't have the field on the board anymore. So there's some conjecture that as long as you fix the finite ramification, then the Galois group will be topologically finitely generated.
That's not known, right?
No, that's not known, but there's a separate condition on the Galois group that Mazur called this condition phi p. That essentially is a substitute for that condition. That means when you're ever doing something p-adically, you can essentially assume this is topologically finitely generated. And so I'm sure I'm using that somehow in saying that you can spread out these things. Yeah, almost really, this is something you can probably find in an immediate paper, and if not, you can find it. I know where you can find it, and you can email me if you're wondering about exactly how that argument works.
What was your final comment that even if they sit well, like But then you cannot spread, I didn't get to the final.
Okay, so. So here's GP to the 33, that's a 33 dimensional space. And here's my rho pi, right? Yeah, so you pick 1 Galois representation and there's 24 families. Okay, so there's 1, 2, 3, 4, 5. And they all here.
We assume that generates a 33-dimensional tangent space.
Yeah, so I assume that the 24 different families generate locally at this point, all 33 dimensions. That only tells me somehow that the eigenvariety for GL4 in this case is responsible for those dimensions at that one point. The infinite Fern was this whole fractal picture that was like moving along the entire, I mean, filling out the entire space. So you like in the infinite Fern process, you start with one automorphic form, you figure out how the tangent space looks there, how many dimensions you have, then you move along one of the families to another automorphic form, and you apply the same principle there. And you keep moving around like this. And so the infinite Fern is more than just like a completely local populations. It's about kind of a fractal picture sitting inside there. And it's about the closure of the countable number of automorphic forms inside the whole deformation space. Okay.
So what can go wrong? Like, you can fill half of it or fill just some components? Like,
Yeah, let me rephrase the question a little bit. You have this huge deformation space. And there's two things you could ask. You could take all of the points coming from automorphic forms, that's a countable collection inside the deformation space, and you could take their closure. Okay. You could also take any Galois representation arising from an eigenvariety, take its points inside the deformation space, and take its closure. For GL2, the infinite Fern process says that the two things are exactly the same. Okay. For GLN, it's known, and also for GL2 over an imaginary quadratic field, that if you only take the automorphic forms and take their closure, you will not get the whole deformation space. There's some automorphic forms that live isolated in the deformation space. But that doesn't preclude the possibility that the eigenvariety itself still is responsible for the entire deformation space. Because what could be happening is like these 24 families have a single automorphic point on them, and then 24 kind of completely non-classical objects.
oh, you really to include those.
Yeah. So the question is whether you need only classical automorphic forms or all p-adic automorphic forms.
No. But if you take a cusp form on GL4 and you take one of these 24 stabilizations, and then you move in a pure direction because you look at three-dimensional things, the classical will be dense in that. I mean, subject to the existence of
Yeah.
this.
So let me repeat a lot of this comment because so if you take one of these automorphic forms on GL4 and you construct a family that is completely contained in this actual set of weights. It doesn't just have that dimension, but it's actually contained in a set of pure weights. Then you will have these kind of zero-sum density statements for the families, and you will construct entire families containing classical automorphic forms. But we're coming at the problem from two different areas, and I'm thinking much more just about like what you can say kind of completely without any hypothesis. And what I would say a lot is that when you said that you could construct a family consisting of pure weights, you were putting a hypothesis on the automorphic form.
Oh, yeah, I do. Yeah.
And so if you can put a hypothesis on the automorphic form, then you're essentially in the situation of the p-adic paper or the element martyr and string paper, and they prove in fact about the infinite Fern in those cases. And again, there's no distinction in these papers between taking the closure of automorphic points in the deformation space and taking the closure of p-adic automorphic points. But that fundamentally uses the fact that those families live over regions of weight space that are consisting entirely of these pure weights. So I given Andre his PDF. I don't know if he's seen it in his email, but he will when he checks it with references. And I give some references, of course, to these things, but also the opposite issue where you can't make these deformation arguments. So there's these papers of Caligari and Gazer, and there's paper for app Polygon Steam is in the case of GL3. When they make computer calculations, like for automotive parts on GL3. I would recommend you look at those papers if the problem interests you.
All right, let's thank John.
And then I think we should also thank Andre and Milada for organizing the conference down here. And I also encourage you all to, if you get a chance, to pop into the office and thank Lisa Driver and the whole staff in the Notre Dame Math Department for providing food and providing hospitality and providing emails. So we can clap for them. I mean, sometimes. I would really encourage you to just pop in and say thank you. I think it'll make their day maybe. And so, or they'll be at the picnic probably too. Right?
Right, so that's what I was about to say. We should figure out how much it's raining outside. It was supposed to rain. And find out what their picnic is. But other than that, I really thank you very much for attending this week. And it was our pleasure hosting you. And let's go.
You understand a lot of like.
No, but okay. If you're not putting a symmetry or on, if you're not putting a